Assalamualaikum. My name is AFIQAH binti JILIS. My metric number is B0810100170. So today I would like to present about Lab 5 Speed Motor Design and Time Response Analysis of Control System Fundamental. So next, I would like to show my MATLAB and my lab sheet. So my lab sheet give figure 3, which is motor speed with proportional controller. So I would like to take my part, which is task 1, implementation of proportional controller. So we need to construct the simulating model. Okay. So I have done my part, which construct the diagram model. So second, we need to run the system by using 3 different proportional gain value, which is 0.5, 3 and 5 to get the output proposed value. So first I would like to change my gain to 0.5, then apply. Okay, next. Then we need to see about the step input, which is step time 0, inertia time 0, final value 1, sampling time 0.01. So clock need to set to 10 and stop time in 1 second. Okay, let's see. So I have changed my step response, which is 0 to 4 step time, inertial value for 0, final value for 1, and sample time is 0.01. Okay, then let's check my clock. So my decimation time is 10. My stop time is 1 second. Okay, so next we need to change the transfer function. So I have put my numerator coefficient, which is 36421.5.541. Next, for denominator coefficient, I would like to put 1 as square, then 112.86635 s plus 1796.2537. Okay, then apply. Okay, so we need to put for 2 transfer function here. Then we need to save as L5 underscore K1. So save. So after all done my part for diagram construction, we need to save. Then second, we need to run. So after 100 finish, we need to write the command window, which is time equal to out.simout.data. Second, K1 equal to out.simout1.data. So why is K1 and why is simout1? So K1 is because lab sheet we need to know as K1 is 0.5, so K2 is 3 and K3 is 5. So for the simout1, first simout is connected with clock. So second out.simout1 is connected with scope. That is why we need to write the 2 function here, simout and simout1. Okay, then we need to write safety as save time. Then we need to write K1 to declare them. For the final step, before the graph is out, we need to write as plot time K1. So enter. So after click the enter, the graph will be out like this. So I name my graph 0.5 is motor speed with proportional controller. Then I label as time at passing at x-axis. Second, I put speed at y-axis. Okay, then first I would like to find my final value real and final value real 1 as I follow as the region. So my final value real as red line is 0.953 at the straight line. So final value real 1 is equal to 0.9110. Okay, next I would like to plot my line at the peak of the line, which is real peak maximum. I will label as TP. Then second, real one peak as maximum value as TP1. Okay, then for the real one peak, I have got my value as 1.141. Second, for the real peak I've got as 1.30. Okay, next I will measure about 1.02C final times with final value real, which is 0.53. So let me calculate. 1.02 times 0.953. I've got 0.97, which is my straight line for input. Second, I would like to find 0.98 times with final value real. So I got as 0.93, which is my straight line with dash line. Then I will put as TS. So my TS point is, my TS value for x-axis is 0.067. So tadi I have got my y-axis 0.933. Okay. Next, I will calculate for value TS1. So I will calculate 1.02 times with 0.910. I've got 0.92, which I met with line dash dot cause it under the red line real. So we can see the difference of line. So second, 0.98 times with 0.9110. So I have got 0.89, which is the yellow line with dash straight line. So this is labeled as TS1. So my value, let me see. Okay, so for x-axis, I have got 0.049 for value x-axis. Then For the y-axis, I have got 0.89. Okay, next. Next, I will calculate about TR1 and TR2. TR and TR1. Sorry. So, for find the value of TR, we have two formula, which is first is 10% and second is 90%. So first we need to find the 10%, which is 0.1 times with final value real 0.953 equal to 0.09. So I have label for the 0.09. Okay, next we need to find the value of 0.9, which is 90%, times with final value real. So I have got 0.85. 0.85 at this point. So I have labeled STR with my double arrow here to here, here to here. Okay. Next, I will find my TR1, which is same 10% and 90%. So 10% is 0.1 times 0.910 equal to 0.092 0.009. So same as the final same as the value here. So I have make a line, straight line, dash, and make it to x-axis. Second for 90% is 0.9 times 0.910. So I have got 0.81. So this is my dash line, which I will make the line down at as this, which is the R1. So the double arrow is from here, yellow line, to yellow line here. This is labeled as TR1. Okay. Okay, after we finish about the graph, so next we need to do the table time response analysis with different proportion again. So for 3 and 5 input, I have done with my label and value. So for the 0.5, let we see. So I have got the value for final value is 0.910. So the peak value for year 1 is, let me see, so I've got 1.141. 1.141. So for the TR, I have got with 0.0 0.81 for the TS. We measured at the x-axis, which is so this is not the final value, so I will check the value, this is correct, whether this is correct or not. So for TS, I've got with 0.049. For TP, I've got with 0.025. Okay, next, let me calculate about percent of OS. So formula that I have used is value peak minus with final value divided by final value and times to 100. So my value peak is 1.141 minus with final value 0.910 equal, then divide by final value again and times with 100. So I have got the percent of OS is 25.38. So to calculate the ESS, formula that I have used is final value minus input. So my final value is 0.910 minus with 0.5 gain. So I've got 0.41. So I have got my question for result and assessment, task 1. So from your observation, what is the difference between result with and without proportional gain? So all I can say is the real line graph is peak, then real one peak is highest than real one peak. This is because what I have seen is when we use the smallest gain, the real will highest than the real one peak. So next for the graph, I have used 3 and 5. So what I have to conclude is when we use the highest proportional gain, we can see the real one line is the highest maximum value compared to the real peak. So that's mean, wait, let us see for 5. So basically for 5 gain is still same with the 3 proportional gain, which is the real one is highest than the real peak. So as I can say is when we use the smaller gain, when we use the highest gain, the real one will pass the real graph. So next we go to the question C. Analyze the system performance for 3 different proportional gain in terms of the time response analysis. So for the time response analysis, I have got with TS 0.049, 0.049, 0.067. So this is same 0.067, 0.077. Next, I've got 0.059 and 0.068. So all I can say is when we use the smallest gain, the time is increased, and when we use the highest gain, the time will decrease. So so we can see from this graph, it more smooth than other graph. So the conclusion is the highest gain that we will use, the smallest time we'll get. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asyraf Afiq bin JAMIL from 2BEY. Today I'm gonna present about the task 2 on the lab 5, speed motor design and time response analysis. First of all, this is the transfer function. This is the simulating model for the task 2. It's just the same with the task 1, but we add on the transfer function filter to get our result in task 2. So first of all, let me show how to follow the, as example, the P3 result, then apply. So we try to run at the stop time of 10 seconds, because at 1 second the result is too slow and we cannot read properly the graph that has been made. And then after we run, we go to MATLAB at the command window, and we plot the graph according to the simulating model that has been made. Data, then save the data. Next, we plot the result for P3, and this is the plain result that we get from the simulating model, and we can adjust the parameter or the properties to get the result easier. Then so for the P3 result, the axis should be good for us to find the value, but let me just alter the y limit to 1.3. Okay, next, first of all, we must find the value of TP, TR, TS, and then for the final value VP. So first of all, First of all, we try to make this is the plot, and then we try to get for the result of the R, which is 0.9 real. We find the axis of Y, which is the nearest to the 0.9. So basically if we want to find the TR, we must use the formula of 0.9 C real 1 to achieve the result, and then 0.9 is timed by 1, which is the input. Yes, this is the input. So we must have the legend to make easier for you to refer. And then for the blue line, we can declare as input, and for data 2 is real, and for data 3 is real 1. Then after we plot the TR, this is the 0.9. This is for 0.9 serial, and to get TR value, we must plot for the 0.1 serial, which is 0.1 times by 1, and we will get 0.1 for the TR1. Then after we get this plot, we should subtract the difference between these two lines, between 0.9 and 0.1, to get the TR value. Then this is the TR value. Then next, to find the TS, TS is the time for the response to reach and stay within 2% of its final value. So we can assume that the final value for the P3 graph is, we must find the value that has reached the stable state. We can assume it right here, and then this is the value for the final value, and then so this is the final value, and then 2% of the final value, and we can assume the TS is at here, like around 0.8, 0.85, around that. Okay. Around 0.93, because it is 2% from the final value. So we can plot lah for the TS, and this is the TS. So for the peak, for the T peak, we can label it on here, on the final value. So after we finish with the simulate model and we get the result, so this is the example of the additional post for the P1. We use the 0.1, we use 0.112s plus 1 at the transfer function for P1. Next we use s plus 50 for the P3, and for the P2, sorry, and for P3 we use 15s plus 1. So if we look at the assessment, first question is, from your observation, what is the difference between result and without additional post? So what I get from this lab is addition of poles to the transfer function has the effect of pulling the root locus to the right, making the system less stable. And if we add the zeros to the transfer function, it has the effect of pulling the root locus to the left and making the root system more stable. Next, for the second question, how the additional posts affect your system performance? So the addition of an extra pole in the left half S-plane cause the system rise time to slow down. As we can see at the graph, the rise time for the less pole or zero pole is decrease or slow down at the left side, but at the addition of a zero in the right half S-plane has a significantly more severe delaying impact than the addition of a pole in left half S-plane. Then for the C, for the third question, identify system type for each additional pole. And for the P1, we have ensured that the P1 is going the under damped process. For the P2 is critically damped, and for P3 is under damped. This is the result for the analysis, for the time response analysis. And for the P1, we cannot find the final value because it has no stability. It has no stable state, which is make us hard to find the final value, and the overshoot percent and with the ESS error percent we cannot find because there is no final value that we can determine on the P1. And next, for the P2, we can get all the result like usual. Just follow the formula that has been given in the lab sheet. And okay, next, this is the plotting data for each input P1, P2 and P3. So this is the complete labeling for the result, and the dominant poles, does the third pole have to be for its effect on the second order response to be negligible? And I assume that for the P3, depends on the accuracy which we looking. However, we assume that the potential exponential decay is negligible after 5 time constant. Thus, if the real pole is 5 times further to the left than the dominant poles, we assume that the system is represented by its dominant second order pairs of pole. So, as the summary, the second order systems are more complex, depending on the values of the system component. The second order system can exhibit 4 kinds of behavior, but according to this lab, we just have the 3 situation or 3 behavior, which is for the P1 is undamped, sorry. For the P2 is critically damped, and for P3 is overdamped. So we found that the poles of the input generate the force response, whereas the system poles generate the transient response. And if the system poles are real, the system exhibits overdamped behavior. Those exponential response have time constant equal to the reciprocal of the pole location. So I think that's all for task 2. Thank you.